You've got a distribution. This is a distribution. A distribution is how some trait is distributed in a population. Guess what? You have looked at a subset, a sample of a population being humans in Columbiana County, and you have measured some trait of theirs. Now, did you get every human in Columbiana County? No. You got, what, between 30 and 40 individuals. It's a relatively small sample. Very often we can't measure something about a whole population. We are not going to go to every human being in Columbiana County and measure their wingspan. It's not going to happen. It'd be entertaining. Hi, we're biology students working on a project. Could we please measure your arm span? I'm imagining like 93-year-old ladies living in trailers on the back of the farm. I'm imagining, people in every place you can imagine. Hi, can we measure your arm span? It's going to get a little strange. So we're not going to do that. But we can measure a sample of the population. This distribution shows us how that trait is distributed. You are going to want to know this. You might even want to be writing some of it down. So this is a time to take a break from answering questions if you're doing that. Let's look at a few of the distributions that we got in this. So here is length of index finger. And here is, that's length of index finger again. Here is circumference of wrist. And here is knee to top of floor. Need to find a better way to stack these. Okay, well let's look at these couple first. So when I look at my distribution, one of the things that we very often do is we lay a sort of imaginary line over it. I'm going to make my line red so it shows up nicely. And we kind of do that. You know what that's called? You can. You don't have to. I wouldn't. It's called a curve. It's called a curve. And for most data sets, for most characteristics, you know where you're going to find most people? In the middle. So let's think about, what was this one, Ian? Length of index finger. So where do you find the highest number of people? Middle length indexed fingers. Some people have pretty stubby little fingers. Some people have really long fingers. They can go model rings for catalogs. There's actually a job. There are hand models. They make a living putting on, jewelry and showing up in ads. I could never do it. I have stubby little hands. We generally find most individuals for most traits somewhere in the middle. And when we draw a line over a curve over data like that, guess what it looks like?
A hump.
A hump. My data has one hump. My data has one hump. My data has one hump. So we call it a normal distribution. That lacks something.
Ours is a normal.
We're going to talk about not normal distributions. When we find our mode somewhere in the middle, and mode, and we were talking about why some of you have a mode that's not in your tallest bar, because your categories are not a single measurement. Could we do single measurement graphing on this? Yeah, we could. We could graph individual measurements, and we would have weirder data. For this data, it works better to cluster it. These are normal distributions. That's an important thing to consider. Normal distribution. Who here thinks that they are above average? Okay, in some way. I'm above average in some ways. I'm below average in other ways. But in height, I am dead stinking average. I am the exact average height for an American female.
I am the exact opposite.
You are a little below average in height. So I am exact average for an American female in height. I am above average. I am overachieving in the weight category. So I'm a little above average. Just means I fall above the middle of the chart. That's all it means. For pinky length, I'm probably below average. I'm probably below the middle of that chart. In any characteristic we want to look at, pinky length, head circumference. Oh, in head circumference, I am so far above average. When I was in high school marching band, they couldn't get a hat to fit me. I have a giant block head. And so, I always have laughed at hats that say one size fits all. I'm like, oh, challenge accepted. And they ended up having to slit the back of a hat and put duct tape over it to get it on my head. You got a tiny head? You got a little pin head? I have a giant noggin. Oh, well, it is what it is. I'm an average height woman with a giant head. It's fine. I'm above average in that category. We all exist above and below average on a whole bunch of characteristics. We can look at a normal distribution for any characteristic in any population. We could go out and look at rabbits and measure ear length. We could go out and look at deer and measure tail length or leg length. We could go look at fish and measure scale count or fin area. You done? For any trait in any population, we can measure it and we can put it on a distribution. So, when we have a normal distribution, where do we generally find the number of individuals with the lowest number of individuals? Where do we find at the ends. So, for instance, there are a whole lot of 5'5" women running around this globe. Are there any 3'1" women? Yes, there are. Are there very many of them? No, there are not very many of them. There are a few, though. Actually, my husband's cousin was at an airport flying here from California a few months ago, and she has a picture because she happened to meet the world's shortest woman. This woman is 21 inches tall.
What?
She's less than 2 feet tall. She has a hormonal condition that caused this. It's a medical condition, but Dawn has a picture. This woman stood up on a little table next to her.
Can we see it?
I don't have it. I should have her send it to me. Yeah. But, there are people who are under 2 feet tall, adult size. Are there any, so we're talking about women here, do you think there are any 7-foot women? Yeah. Not many.
Yeah.
Not very many, but there are a few. And again, at both ends of that range, very often it indicates an underlying medical problem. So for instance, the man who held the record for world's tallest man actually had a pituitary condition. His pituitary gland was releasing too much growth hormone, and he died pretty young because there were other medical problems that went along with that. Now he was 8'2" tall when he died. That's why he's holding a cane, yeah. And if you look at his legs, his knees look a little odd. His knees look like they're bending in sort of ways that they maybe shouldn't, that aren't real comfortable. Aside from having a real hard time buying clothes, because that's somebody who has never walked into a store and bought clothes in his life, basically. So aside from that, that is an expensive life. Yeah. Here's the thing to think about, and this is sort of like biology class as also philosophy lesson and like perspective on life lesson. Being average really kind of rocks. In a lot of ways. The world is set up for average. So the world is really built for everybody in this part of the graph. You can be a little shorter, a little taller, a little lighter, a little heavier. When you get out to these ends, life is expensive and difficult. And this is also, you have lots of company here. What's the show called? Little People, Big World? And it's the family of dwarfs. And then I think they have 2 full-size children. And then they have some children who are also little people. It's genetics. We'll talk about it when we get to genetics. It's genetics. It's recessive. So you can have, or it's not a recessive trait, so you can have 2 affected individuals who have a normal-sized child. For those people, they also, when they walk into any house built for most humans, things are too high, things are too, you think that guy could walk comfortably into your house? No. The tall guy. He needs cathedral ceilings. Everywhere. That is an expensive and difficult life.
How would you get the money in order?
Are there people on either end of this distribution? Yeah, there are. Are there very many of them? No, there are not. There are a whole lot of humans who fall right in there. And so the world tends to be built for us. Now, let's look at some of the other data you guys got. So here is distance from top of knee to floor. What does that show? Howdy, sir. So, let's look at this knee to floor data. Knee to floor data. Is that a normal distribution?
No.
No. It's a skewed distribution. What does that tell you? Do we have a lot of people with really long calves here?
No.
No, we have a lot of people with really short calves. That's kind of weird. So, do you think that leg length or calf length is connected to any other data that was collected? Our height data, is it a perfect match to our leg length data? Nope, that's not it. No, but it's not terrible. It's not terrible. Where is that? Is that this one? Yeah. So, we still don't have a whole lot of people in the upper ranges in either set of data. We don't, now, interestingly enough, we've got quite a few people in the middle here and very few people in the middle here. We can look for patterns in the distributions of traits. Now, let me ask you this. Do you really think that, let's look at this height data. This is sort of like an inverse graph here. Do you really think that people here at Beaver Local are all that short? Or is it who we measured? Yeah, it's who we measured. The other class got Mr. Sechrist. If you had showed up, let's see. Now, for females, there's not as much of a difference in height between freshman and senior year. For males tend to put on height later. So a lot of males are still growing right up till the time they graduate or after they graduate. So if we had measured a lot of senior male students, do you think that that would change our distribution for height?
Yes.
Probably. The best way to get the closest you can get to an actual distribution that reflects your population is a big sample, randomly chosen. What wasn't random about our sample?
The measurements.
No, in terms of who we chose.
Oh.
You only measured students, for one thing. You may have measured teachers, but your entire population was confined to this high school. If we're saying this is representative of everybody in Columbiana County, it's not, clearly. We didn't measure any old people. We didn't measure any little people. We didn't measure, we had everything from, we probably snagged a few 14-year-olds. We probably had a few 18-year-olds. We've got, most of our population that we sampled was between probably 14 and 18. Okay, so what would happen if we went out and we really got a good random sample? Like we went to Giant Eagle in Calcutta and we asked every 10th person who walked in the door, hey, can I measure your wingspan? Hey, can I measure your height? Would that be a more random sample? Yeah. And if we got 100 pieces of data, I'm going to bet you that our height distribution would start to look more like that. Because in general, for any trait in any population, what we tend to see is a normal distribution. Sometimes we call this a bell curve, but this is pretty common. For ear length in rabbits, for leg length in deer, for tail length in horses, for height in humans, normal distribution is pretty common when there's pressure on the population. All that evolution is, it is a shift in the distribution of traits in a population. Has anybody here ever been to a museum and looked at medieval armor? Okay. 1. We'll pull up some pictures at some point. When we go to the Carnegie, if you make a point to go over to the art wing, I think they have a little bit of armor over there. And you're looking at, these are knights, these are big guys, these are nobility. These are important, powerful men, and they're all about this tall. I'm looking at the tops of the armor.
No.
Because average height for humans has changed. Humans have been getting taller for a couple, at least we know, at least about 1,000 years, and probably a little longer than that. Now, part of it's better nutrition. We have all the calories we could ever want and then some. But there also seems to be a selection towards height. So over time, what has happened? Well, if we looked at the Middle Ages for height, and we'll take just males for now. Maybe averages here. And then if we look 200 years ago, maybe averages here. And then if we look now, maybe averages here. The distribution is changing. That's evolution. So that's all evolution is a change in the distribution of traits over time.